Hello friends, how are you? This is Ethiopedia by Desu Birchit. In this video, we are going to discuss assignment problem with maximization objective. The past four videos of assignment problem were focused on minimization objective, but in this video, we will discuss application of Hungarian method for solving maximization problems. Let's start with the problem. An enterprise planned to maximize its profit by assigning 5 sales personnel to 5 sales territories. The data below indicates the profit in BIR generated by assigning a certain salesperson to a given sales territory. Find the optimal assignment schedule by using Hungarian method. In the given matrix, the rows represent the salesperson and the columns represent the territories where the salesperson is going to be assigned. The matrix entries represent the profit generated in BIR by assigning a certain salesperson to a given sales territory. As we discussed in part 1 of this installment, before applying the steps of Hungarian method, we have to convert maximization problem into minimization problem by calculating the opportunity loss. Opportunity loss is calculated by deducting every element in a column from the biggest element in that particular column. Opportunity loss calculation can simply be considered as the reverse of column reduction calculation. In column reduction calculation, we deduct the smallest element in a given column from every element in that column. But in case of opportunity loss calculation, we deduct every element in a given column from the biggest element in that particular column. To carry out the opportunity loss calculation, let's identify the biggest element in each column. The biggest element in column 1 is 58, column 2 maximum is 60, column 3 maximum is 59, column 4 maximum is 58, and column 5 maximum is 59. Let's insert a blank 6x6 table at this right-hand side for the new entries and continue the deduction starting from column 1. That's 58 minus 56 is equal to 2, 58 minus 58 equal to 0, 58 minus 52 equal to 6, 58 minus 48 equal to 10, 58 minus 54 equal to 4. In column 2, 60 minus 55 equal to 5, 60 minus 57 equal to 3, 60 minus 49 equal to 11, 60 minus 55 equal to 5, and 60 minus 60 gives us 0. In column 3, 59 minus 54 equal to 5, 59 minus 52 equal to 7, 59 minus 53 equal to 6, 59 minus 59 equal to 0, and 59 minus 56 give us 3. In column 4, 58 minus 50 equal to 8, 58 minus 51 equal to 7, 58 minus 57 equal to 1, 58 minus 56 equal to 2, and 58 minus 58 equal to 0. In column 5, 59 minus 49 equal to 10, 59 minus 59 equal to 0, 59 minus 56 equal to 3, 59 minus 51 equal to 8, and 59 minus 52 equal to 7. It is this right-hand side matrix, it's called opportunity loss matrix, that we use in the upcoming steps of Hungarian method. The first step of this method is row reduction and column reduction. As the first sub-step of this step, reduce the initial matrix by subtracting the smallest element in each row from every element in that row. For this reduction calculation, let's identify the smallest element in each row. The smallest element in row 1 is 2, the smallest element in row 2 is 0, row 3 minimum is 1, row 4 minimum is 0, and row 5 minimum is also 0. Also, let's copy a blank 6x6 table at this right-hand side for the row reduced entries. And let's continue the calculation starting from row 1. That's 2 minus 2 equal to 0, 5 minus 2 equal to 3, 5 minus 2 equal to 3, 8 minus 2 equal to 6, and 10 minus 2 equal to 8. In row 2, the minimum is 0. Subtracting 0 from every element in that row will not change the values of that row. Hence, we can copy row 2 elements as they are. In row 3, 6 minus 1 equal to 5, 11 minus 1 equal to 10, 6 minus 1 equal to 5, 1 minus 1 equal to 0, and 3 minus 1 gives us 2. We can also copy row 4 and row 5 values as they are, because the minimum value of each of these rows is 0, and hence deducting 0 will not change the values. The second substep of this first step is reduce the row reduce matrix by subtracting the smallest element in each column from every element in that column. The minimum value of each of the 5 columns is 0. Thus, since deducting 0 will not change the values, we will skip the column reduction calculation and cast forward to step 2. Actually, it's logical to expect the minimum value of each column is 0 because opportunity loss calculation yields at least 1 0 per column. Step 2, row scanning and column scanning. In this step, we will find the minimum number of straight lines that must be drawn through the rows and columns of the reduced matrix so that all the zeros in the matrix will be covered. Again, this step has two sub-steps. First, examine the rows of the reduced matrix successively, and whenever a row with single zero is found, enclose that zero with rectangle and eliminate a column containing that zero by drawing a vertical line through it. If a given row contains no zero or more than one zero, we will skip it. So let's scan the rows starting from row 1. Row 1 contains only one zero, that's the zero under column 1. So we will enclose this zero in rectangle and we will eliminate column 1 by drawing a vertical line through it. The only undeleted row of row 2 is the one under column 5. So we will insert this zero in rectangle and we will delete column 5. Also, we can enclose the only zero of row 3 in rectangle and delete column 4 by drawing a vertical line through it. The zero at the intersection of row 4 and column 3 is the only zero of row 4. So we can insert this zero in rectangle and eliminate column 3 by drawing a vertical line through it. The only zero of the ultimate row is the one under column 2. Enclose this zero with rectangle and delete column 2. This row scanning sub-step helps us to cover all the zeros in the matrix by the minimum number of straight lines. So no need to go to column scanning process. Rather, we can cast forward to the requirement that specify what should be done next. If the minimum number of straight lines drawn to cover the zeros is the same as the number of rows or equivalently columns, the solution is optimal. Hence, an optimal assignment by referring the zeros inside the rectangle can be made. Otherwise, go to step 3. The number of rows or columns in the given matrix equal to 5. The number of straight lines drawn to cover the zeros equal to 5. That's 5 vertical lines. Since the number of straight lines drawn to cover the zeros is equal to the number of rows, the solution is optimal. Thus, an optimal assignment by referring the zeros inside the rectangle can be made. For this assignment, let's draw a table containing 3 columns and 7 rows. The 3 columns stand for demonstration of salesperson, sales territories, and profit generated by each salesperson. The 7 rows stand for title of columns, the 5 salespersons, and the total optimal profit. Let's copy the matrix we produced after going through the steps of Hungarian method and the given matrix at this right-hand side in order to refer the assignments and the profit generated by the salesperson in a given sales territory. Salesperson 1 is assigned to sales territory 1. Salesperson 1 generates 56 per profit when he or she is assigned to sales territory 1. Salesperson 2 is assigned to sales territory 5. Salesperson 2 generates 59 per profit when she or he is assigned to sales territory 5. Salesperson 3 is assigned to sales territory 4. Salesperson 3 generates 57 per profit when he or she is assigned to sales territory 4. Salesperson 4 is assigned to sales territory 3. Salesperson 4 generates 59 per profit when she or he is assigned to sales territory 3. Salesperson 5 is assigned to sales territory 2. Salesperson 5 generates 60 per profit when he or she is assigned to sales territory 2. Optimal profit equal to 56 plus 59 plus 57 plus 59 plus 60, which is equal to 291. The formula: optimal profit is equal to the sum of row minimum plus the sum of column minimums plus the smallest element chosen to add on or subtract from other elements. Can't help us to check the correctness of this optimal 291 because the minimum values are not derived from the given matrix. Rather, we derived them from the matrix of opportunity loss. Thus, in such cases, the calculation gives us different results. By this, I conclude this section. If you follow all the 5 installments of assignment problem I uploaded, with no doubt, you will master the subject matter. You know why? Because this installment covers the entire spectrum of assignment problems, thus balanced assignment problem and unbalanced assignment problem, restricted assignment problem and non-restricted assignment problem, Hungarian method with and without diagonal rule, assignment problems with minimization objective and maximization objective. Hope you will enjoy all the contents. Don't forget to subscribe, like, and share the page. Bye-bye.